All right, class. So we're ready to do section 8.5, which is titled the dot product. So the very first thing I just have here the definition of the dot product. So if we have two vectors, vector v and vector w, then the dot product is the following, right? So essentially you take the horizontal components, multiply those together, and add it to the product of the vertical components. Right? And something to note here is that the dot product of two vectors is a scalar, right? So we don't get a vector back. We actually just get just like a value, right? Just like when you take the modulus of a vector, the length, right? That's not a vector, that's a scalar. Right, so then I just have some practice here. So if vector v and w are the following, let's find v dot w, w dot v, v dot v, and then lastly the modulus of v, right? So v dot w is equal to -2 times -3 plus 6 times -1, right? Just following that formula from above. So this gives me what, +6 minus 6, which equals 0, right? W dot v would be -3 times -2 plus -1 times 6, right? We just switch the order around, right? Because w comes first, right? So just following that equation from above, this gives me a +6 minus 6 again, which of course is 0, right? And then v dot v would be equal to, -2 times -2 plus 6 times 6, which equals 4 plus 36, which equals 40. Right? The modulus of v is equal to the square root of -2 squared plus 6 squared, which equals the square root of 40, which this simplifies to be, we can do radical 4 times radical 10, which equals 2 radical 10. Right? So A, B, and C, just some new, just using the dot product, and then the modulus of V, something we've done before, right? So then here's some properties of the dot product, right? And I can show the first one for you. So property 1, like a mini proof of that. So if we let vector v equal the vector a1 comma b1 and vector w be a2 comma b2, right? Then if I take vector v dot vector w, this is equal to vector a1 comma b1 dot vector a2 comma b2, which is equal to a1 times b1 plus, that would be a2. Sorry about that. a1 times a2 plus, and then b1 times b2. Right. So remember these a and b components, these are just real numbers. So I can rewrite this just by changing the order of the factors. Right. This is using, the commutative property of multiplication of real numbers. Right. So then, this is just the same thing as, vector a2 comma b2 dot a1 comma b1, which is equivalent to vector w times dot product vector v, right? So that shows property 1, right? So in other words, the dot product is commutative, is what this is showing us. Right, so this has commutativity for number 1. Number 2, it's showing us that the dot product has associativity with a scalar. And then number 3, you can see what that's showing us is the dot product has like a distributive property. And then number 4, if you take the dot product, v times phi, that's the same thing as the square of the modulus of v. Number 5, we have basically like a multiplication property of 0. If I take the 0 vector times a vector v, that just gives me back a scalar of 0. And then lastly, number 6, that's essentially showing like some associativity with a scalar, right? Well, I guess also kind of like a commutative as well, that I can take that c and multiply it with the v, or with the put it with the w, right? So those are just some properties of dot product. Right, so page 2, we're starting objective 2, which is find the angle between two vectors. So now that we know what the dot product is, one useful thing of the dot product is using this equation presented in the purple box, so we can figure out the angle between two vectors, right? And notice they have to be two non-zero vectors, v and w, right? Because we're dividing by the modulus of v times the modulus of w, so neither one of those can be 0 then, right? So if you're interested to see a proof of like, where this formula comes from, you can look on page 789 in your text. It's going to utilize the law of cosines in order to show that proof. It's not too hard to follow, so you can check that out if you're interested. For time's sake, I won't go over that proof in this video. So then, example 2, we're asked to find the angle between vector v and vector w, round to the nearest tenth of a degree, right? So something to keep in mind is, with this is if cosine of theta is positive, right? What that's going to tell me is that, if we're thinking about, all students take calculus, right? That theta is going to be in between 0 degrees and 90 degrees, right? If cosine of theta is less than 0, in other words, if cosine is negative, we're going to be, in the second quadrant, right? Because, the angle between two vectors is going to have to be, something between 0 and 180 degrees, right? So that would be, theta would be in between 90 degrees and 180 degrees, right? And then if cosine of theta actually equals 0, then theta is equal to 90 degrees. Oops. Right. So then, if you think about this a little further, if cosine theta, so we're thinking about this equation here, if cosine theta is positive, what's going to drive this sign of this is what v times w is, right? Because if you think about the bottom, the modulus of v times the modulus of w, that's always going to be a positive number times a positive number. So there's always going to be a positive number on the bottom. So depending on what v times w is on the numerator, that's going to drive if the sign is positive or negative, right? So obviously in this case, this is when vector v dot vector w is greater than 0. This, these next two, this is going to happen when vector v times vector w is less than 0. And then lastly, when theta is 90, is going to occur when vector v times vector w is equal to 0, right? And we're going to see in a little bit that this last scenario is a special case, and we give that a special name. So we'll go over that in a moment. We call that that vector v and w are called orthogonal, right? All right. So let me just erase this. got in the way of example 2. So example 2 asks us to find the angle between vector v and vector w round to the nearest tenth of a degree. So, using that equation, cosine of theta is going to be equal to vector v dot vector w divided by the modulus of v times the modulus of w. So vector v times vector w is going to be equal to 5 times negative 5 plus negative 1 times 12, which equals negative 25 minus 12, which equals negative 37, right? So this is less than 0. So, following up here, that's going to tell me that theta is in between 90 and 180 degrees, right? So then, that's just going to be my numerator, negative 37. So now we need to figure out the denominator. So let's find the modulus of vector v, which would be the square root of 5 squared plus negative 1 squared, which equals the square root of 25 plus 1, which is the square root of 26. All right, so I'll just fill that in. So now we need to find the modulus of vector w, which is equal to the square root of negative 5 squared plus 12 squared, which equals the square root of 25 plus 144, which equals the square root of 169, which equals 13, right? So just note that, like I was saying, that this is less than 0. So, so what that tells me is that theta is in between 90 and 180 degrees. Right? And we can see that a little more clearly if I graph these vectors. Right? So vector v is 5, negative 1. So 1, 2, 3, 4, 5. I think I'm going to go increase these by, by 2's on the y-axis. So 5, that terminal point would be 5, negative 1. So then, let's see if I can draw this. That's vector v. And then, let's see, vector w is negative 5, 12. So 2, 4, 6, 8, 10, 12. And negative 5 is the x-coordinate. 2, 3, 4, 5. Right, so there's vector w. So you can see that the angle in between them is going to be bigger than 90 degrees, right? In between 90 and 180 degrees. So that's what we're trying to find, is theta. So what we know is that cosine of theta equals negative 37 over radical 26 times 13. So theta is going to be equal to arc cosine of negative 37 over radical 26 times 13. Right, so you can plug that in your calculator, make sure you're in degree mode, and round to the nearest tenth, you get 123.9 degrees, right? So this guy is 123.9 degrees. Right, so then on page 3, I just pulled out some terms so we can look at. So it says here the terms orthogonal, perpendicular, and normal all refer to objects where the measure of the angle between them is 90 degrees. Right, so by convention we say that two lines in a plane are perpendicular. right? So like this first example. And then when we have we say that two vectors in a plane are orthogonal, right? So notice we have two vectors and they share the same initial point, right? Their heads oops, sorry, I lost my train of thought. So their initial points together, right, and they make a 90-degree angle in between. And then lastly, if we have a vector and a plane, so if the vector, like 90-degree angle to the plane, so like a plane's like an infinite sheet of paper, right? We call that normal, right? The vector's normal to the plane, right? So the next thing we have is just a definite, something useful to help us, a statement for determining if two vectors are orthogonal. So this is another nice thing about dot product. So two vectors are orthogonal if and only if their dot product is equal to 0, right? And if and only if, remember, this means that the statement goes both ways, right? So if I know this is true, I can conclude that they're orthogonal, or if I know they're orthogonal, then I can conclude this statement's true, right? It goes both directions, right? So example 3, we're asked to determine if the given vectors are orthogonal. So to do that, we just take the dot product of vector v and vector w, which would be 4 times 6 plus 3 times -10, which equals 24 minus 30, which is equal to -6, which is not equal to 0, right? So these are not orthogonal. And then to see if S and T for part B are orthogonal, we're going to find the dot product of those two. So we take -2 times 11 plus 1 times 22, which equals -22 plus 22, which does equal 0, right? So these are orthogonal. Right. So that's all there is to determine if two vectors are orthogonal or not. So on the next page, I have some information. So we're going to talk about decomposition of a vector into orthogonal vectors. So, two vectors that meet at a 90-degree angle. So if v and w are two non-zero vectors, then the following is true. Number one, the vector projection of v onto w is given by projection v onto w equals, so we take the dot product of the two in the top and then divide by the modulus of w squared, and then we multiply that times vector w. So this part is going to be a scalar, right? So we're taking a scalar times a vector, so that will give me back a vector, right? So then to decompose vector v into vectors v1 and v2 that are parallel to w and orthogonal to w respectively, then we get the following, right? So what this does is gives us like x and y vectors of the vector, right? And this is actually really useful like to physics, right? So then we just have some equations here to find v1 and v2. So v1 is going to be equal to the projection of v onto w, and v2 is just equal to v minus v1, right? So we're going to use these in some applications here in a moment. And then just to kind of help visualize this, so if we have vector v here, this pink vector, going at some angle, then if the sun is shining in, straight down, so perpendicular, or in other words, orthogonal to w, projection of v onto w is simply the shadow casted by vector v, right? So the sun rays are going to hit, and then this part is going to be like a shadow of that, and that part is v1, which is the projection of v onto w, right? So then this is just another statement from the text. So to decompose a vector into two orthogonal vectors, we use the idea of a vector projection. So consider the two vectors v and w drawn with a common initial point A. Suppose we want to decompose v into vectors v1 and v2 that's parallel to w and orthogonal to w respectively. We call vector v1 the projection of v onto w and denote v1 by projection v onto w. Right? So you can see we have two different cases here where theta is acute and where theta is obtuse. Right? You can see both cases and how that looks, right, in the figures below. Right? So it's kind of like casting a shadow, right, the projection. Right? So now let's practice using the equation. So we're given vectors v and w. In part A, we want to calculate the projection of v onto w. So that's equal to the dot product of v and w divided by the modulus of w squared times vector w, right? So this would be equal to what, -5 times 2 plus 4 times 4 all over the square root of 2 squared plus 4 squared, all this squared, times vector w, which is 2, 4, right? So this would be equal to -10 plus 16 all over. So this square just gets rid of the square root, right? So we'd have 2 squared plus 4 squared, which is 4 plus 16, which is 20, times vector w, so 2, 4. And then this would be equal to 6/20 times 2, 4, which is equal to 3/10, right? Divide top and bottom by 2 times 2, 4. And then multiplying the scalar through, right, that would give me 3/5, 6/5, right? Reducing that. So we take 3/10 times 2, then 3/10 times 4, and simplifying that, we get this vector, right? So that is the projection of v onto w. So then part B, we want to find v1 and v2 essentially, right, where v1 is parallel to w and v2 is orthogonal to w, and we know v1 plus v2 equals v, right? So remember, vector v1 is equal to the projection of vector v onto w, which we found that from part A to be 3/5, 6/5, right? So that's from part A. So then vector v2, right, remember, is vector v minus v1, right? So vector v is -5, 4, and v1 is 3/5, 6/5, right? So we can get a common denominator, so this would be -25 over 5, 20 over 5, right? Because everything in my second vector has denominator 5, right? So this would be equivalent to -28/5, right? Because we take -25 minus 3/5, and then comma, and then 20/5 minus 6/5 is 14/5, right? So this is vector v2, right? And there's vector v1. So we found both of those, right? So now we're going to do a couple of applications. So example 5 is we have a truck weighing 2,000 pounds. It's parked on a hill with a 10% incline. And we have a picture here. So part A says, write the force vector F representing the weight of the truck through a single tire. Write F in terms of I and J and assume that the weight of the truck is evenly distributed among all 4 tires, right? So you can see here, in the diagram, that's actually the answer for part A, right? But let's think about how we came up with that. So notice it's saying that F represents the weight of the truck through a single tire, right? So if we take the total weight of the truck, 2,000 pounds, and then divide that by 4 tires, we get 500 pounds per tire, right? So the vector, is going to go straight down, right? Weight always goes straight down, the vector weight. So if you take physics, you'll know that. So vector f, right, is this vector is going straight down. So that's just going to have a j component. And since it's going downward, it's negative. So it'd be negative 500 times vector j. Right, so that's where that comes from. So then part B says find the component vector of f parallel to the hill, round to 1 decimal place. So in other words, what we want to find is f1 from the picture, right? So just to make this more clear, let's say let vector f1 and vector f2 be the components of vector f parallel and perpendicular to the hill respectively, right? And then we'll say let vector u equal cosine of 10 degrees times I plus sine of 10 degrees times j. B, the unit vector in the direction up the hill. Right, so that's this vector u here, right? That's drawn. So then what that allows us to do is to say that vector f1 is going to be equal to the projection of vector f onto vector u, right? So this would be equal to vector f dot product vector u over modulus of u squared times vector u, right? So that gives me, so just plugging this in, we get 0i minus 500j dot cosine of 10 degrees times vector I plus sine of 10 degrees times vector j all over the modulus of u squared, right? But it's important to note that since u is a unit vector, the modulus of u is just equal to 1, right? So this would be 1 squared, and then we would have times vector u, which is cosine of 10 degrees I plus sine of 10 degrees j, right? When I'm saying times there, I mean the dot product, right? So then what this gives me is 0 times cosine of 10 degrees plus negative 500 times sine of 10 degrees all over 1 times cosine of 10 degrees times vector I plus sine of 10 degrees vector j, right? So this turns out to be approximately, so if we round the cosine and sine of 10 degrees, what we end up getting is negative 86.8 times cosine of 10 degrees times I plus sine of 10 degrees times vector j, right? And this gives me approximately negative 85.5 times I minus 15.1 times vector j, right? So that's just taking, the scalar times each piece, right, and rounding that, so that's what we get, right? So that's what we were asked to find in part B. So then part C, we're asked to find the magnitude of the force required by the brakes on each wheel to keep the truck from rolling down the hill, right? So, F1 is the vector is essentially going this way, right? Well, the same amount of force is going to have to go in the opposite direction to keep the truck from rolling down the hill, right? So that would be the force being exerted from the brakes, right? And notice it's going to have to be the same in magnitude, but just the opposite direction, right? So in other words, if vector B is the vector for the brakes, that's going to be equal to -1 times the vector F1, right? So that's going to be equal to negative times negative 85.5i minus 15.1j, which this equals 85.5i plus 15.1j. So then what we're asked to find is the magnitude of the force, right? So that's the modulus. So we'd take the modulus of vector B, which is equal to the square root of 85.2 squared plus 15.1 quantity squared. And this comes out to be approximately 86 let's see. I wasn't told to round to a certain amount. Let me throw this in my calculator real quick. I forget. 85.2 squared plus 15.1 squared. Yeah, it comes out to be around 86.5 roughly. Right. Or wait, excuse me. I wrote down 85.2 here, but that should be 85.5. That's why that's working off weird. All right, so this comes out to be roughly 86.8, right? So if we just make that correction. All right, so we answered that problem. And then the last concept here, and we have two examples with this, is using vectors to compute work, right? So work is another idea from physics that we can use projections and dot products to help us find. So if D is the displacement vector of an object and moving the object in a straight line from points A to B under a constant force F, then the work done is computed by the following. So work is equal to the dot product between the constant force vector and the displacement vector. And then number 2, right, says that the work is equal to the modulus of the projection of F1 to D times the modulus of D. Or in other words, we can take the modulus of F times the modulus of D times cosine theta, where theta is the angle in between F and D, to find work as well. Right. So we can work through example 6. So it says find the work done by a force F, which is equal to 2I plus 7J, and that's in newtons. And moving an object in a straight line from point A to B, assume that the units in the coordinate plane are in meters. Right? So the displacement vector here is going to be equal to the vector AB. Right? So that vector, we can compute that by taking 9 minus -1 times vector I plus 11 minus 5 times vector J, right? So this would be equal to 10I plus 6J, right? So then the work, oops, that's not a vector, just the work is equal to vector F dot product vector D. And just to note that this is measured in newtons and this is measured in meters. Right, so we would take 2I plus 7J dot product 10I plus 6J, which this equals 2 times 10 plus 7 times 6, which equals 20 plus 42, which equals 62. And the units here are newtons times meters, right? Newton meters. Right. So then the last part, example 7, we have a dog pulling a sled 200 feet across a yard on a horizontal path. She exerts a constant force of 25 pounds directed upward 15 degrees from the horizontal. Find the work done round to the nearest foot-pound. Right. So essentially, let me draw maybe a little picture here. So here's A, here's the point B. So we're going from A to B. And then we have some force F going upward, and that's at an angle of 15 degrees. Let's see, so this whole distance from A to B is 200 feet. Right, we're given that here. And then let me actually draw vector F up a little bit. So then if I pull this straight down, right, where that's at a 90-degree angle, then this blue vector, this whole vector here is, the displacement vector, vector D. So that blue vector there, that's equal to the projection of vector F onto vector D. Right, so there's just kind of a picture there. So if we use those equations for work, so line item number 2, we would have that work is equal to the modulus of the projection of vector F onto D times the modulus of vector D. But that's the same thing as the modulus of F times the modulus of vector D times cosine of theta. So theta is 15 degrees, right? So that's an easier form. This is an easier form of us to use, right? So just using this equation here. So then we get, 25 pounds, right? So I know that, so this part here, so she exerts a constant force of 25 pounds. So what that tells me is that the modulus of vector F is equal to 25 pounds. Right, and then of course vector D, the displacement vector, that's going to be equal to 200 feet. Right, so if we just plug those in, we get 25 pounds times 200 feet times cosine of 15 degrees. So this gives me so this comes out to be 4,830 if we round to the nearest foot-pound, right? Because foot times pound is the unit. So there's my solution, right? So we end up using the second form of that, a little easier to work with, right? So that's the amount of work done with the dog pulling the sled, right? All right, so that's all I have for that section. Let me know if you have any questions.